So, I am Iaakov from Jerusalem College of Engineering. I'm going to talk about linear software models. And our story begins with Farmer's modularity paper 1972. I hope you have, you are familiar with it. And our point of view is that if we are going to put a few copies of the Curiosity satellite on Mars, and there is a bug there in some of the Curiosity samples, then there should be automatic ways to correct the problem. And so my view is automatic runtime system composition from ready-made software components. I view software as systems and components. Systems doing systems, components doing components. Systems do not need to program at all. Okay, agenda not needed. So, the problem. There is a design system and purchased components. How to match those? The design system is described in terms of modules, and we invented two terms, structure and functional. So a structure is a generalization of structs, classes, and so on, and they are supposed to remind us of vectors. And functionals are potential functions that may be invoked, not necessarily. The purchase components also have structures and functionals, but the logic of the component manufacturer is different. It is its technology, not the system. And they are requirement units. So we must match similar things, but with a different underlying logic. The problem is structures provide different functionals, then both are needed. If they provide the same functionals, they are redundant. If there is a partial overlap, we must choose a linearly independent set of structures. We get to a modularity matrix. So what I'm trying to do in this theory is to take familiar terms of software engineering and put them in terms of really plain mathematics, linear algebra. So I don't need to invent new mathematics. I don't need to convince that the mathematics is correct. And I don't want to speak vaguely. Example. This is an introductory example. Suppose there is output feedback encryption. Doesn't matter if you are familiar with that or not. There is a way to do encryption of long messages. You cut them and do some preprocessing, encryption, and some XORing in a certain order. I make a list of functionals and a list of structures. The functionals are a specific random number generator, a specific encryption function, say RSA, XOR is a logical function, preprocessing, fetching, and having this appropriate size. What are the structures? A set of random distributions, encryption protocols, logical functions, which include the desired XOR, and a processor structure providing preprocessing functions. I put them in a matrix. Here it is. These are functionals, these are the structures. Problem. The problem that this line and this line are linearly dependent. We want to change the system because we would like to have only linearly independent functionals or structures because we want to make efficient the software system. It is a requirement of the software design and development. We can reorder the functions, and if we do that and introduce some additional, we separate the preprocessing, then we have a new kind of matrix in which there are no two rows that are linearly dependent and no two columns that are linearly dependent. And the general aspect of this matrix is block diagonal. This was an example to have the feeling of how it looks. Now, the theory. I define a modularity matrix, a Boolean matrix, asserting links between functionals and structures. Independent structure, it's a vector, a column vector, non-empty proper subset of functionals, and is linearly independent of other columns. The same for functionals, non-empty proper subset of structures. This is the row, and is linearly independent of other rows of the matrix. First theory. Up to now, there were definitions. A well-composed modularity matrix in which all the functionals are independent and the structures are independent, the matrix is square. Easily proved. Now, schematically, a block diagonal matrix looks like that. Theorem 2. In a well-composed modularity matrix, obeying theorem 1, in which union set for a given set of functions is disjoint to other functional union sets, it is reducible, it can be put in block diagonal form. We also define diagonality expressions to calculate how close to the block diagonal matrix we are, and our definition is a trace minus an off-diagonal term. If you need further details later on, we can talk. A linear reducible model is characterized by a well-composed and reducible matrix. The number of modules at each level is the number of blocks of that matrix. A single responsibility principle, which appears in all those books as a recommendation, now it's a theorem. The theorem is each structure column intersects a single module. It's a theory, clear one. Okay, in order to corroborate the theory, we wanted to show that canonical systems and real systems obey the theory. First one, Parnas quick index. Parnas suggested two modularizations. Here is one. This is the second one. We calculate the diagonality of those matrices, and we get to the same conclusions of Parnas formally. Second example, observe a design pattern. Here is the matrix. And this array is subject, this array is observer. This is taken from the Gang of Four book. So this is the same application, analog and digital clocks and so on. The matrix has the same format. Now, big examples, real examples. This grid, network earthquake, engineering simulation, University of Illinois. We extracted data from reports of the project. Every time we did such matrix with some information from the literature, it's completely scattered. So we rearrange blindly the rows and columns. This is the result. Now, we have a few outliers, but the outliers are very close to the blocks. So we call this border linear model. Now, soon we will have a discussion of the open questions and what are the meanings of the outliers. We have done this for several systems. Okay, discussion. We have a model. We can translate familiar terms of software engineering like coupling. Coupling is defined in terms of a matrix, corroborated exactly by canonical systems and approximately by real large systems. Our matrix is small and meaningful. There were matrices, other matrices suggested in the literature, but they are much bigger and they have problems. And we are in the way to automation. Now, open questions. First, we don't know whether the outliers are because there are systems of this kind in the reality, or because they were developed before our theory. And if they were developed in applying our theory, we would get strictly block diagonal. We don't know. Okay, I think that's enough. We have some time for questions or not?
No, we'll save the questions, unless there are any clarifying questions. Yes, we have one here.
When you're talking about coupling, you're trying to decide if two modules are coupled. What is your definition of coupling that you're using in there? Is it control coupling or data flow coupling, stamp coupling? I didn't quite understand that part.
Okay, part of the theory is that if something doesn't fit the theory, we shall throw it out. So I want to see the conclusion. We use the couple in a precise new meaning, enabling linear independence. That's all. So take your several kinds of couplings and you see whether they can be expressed in terms of linear independence. If not, tell me. That would be interesting. If not, if it is important, please tell me.
Yes?
Are the number, excuse me, are the number of functions always equal to the number of structures?
No,
So why do you get square blocks?
No, if the structures and functionals obey linear independence, we get such a matrix. This is a result of this theory.
Yes, but I can see that, but when they're not the same.
You should ask why they are not the same.
Yeah, well, that is exactly, that's what I'm asking.
No, for a specific system.
I see your point, yes.
You should ask, and again, the same, if there is a good example of rectangular, inherently rectangular system and not square, please tell me, because this is a challenge to the theory.
Okay, I think that this is as good as far as we can get with the clarifying questions.